Allora, benvenuti a tutti a questo colloquio che sarà tenuto da Camillo De Lellis, che non avrebbe bisogno di presentazione perché oramai è una persona a tutti noi ben nota. Voglio dire che sono molto contento che Camillo comunque è entrato a far parte dei faculty del GSSI dal 1° ottobre. So I switch to English now. Welcome to everybody. I want to thank you everybody to be here, and I'm happy to introduce Camillo De Lellis' colloquium lecture. And Camillo recently, as you know, joined the GSSI since October 1st. About Camillo, I should spend 1 hour talk to illustrate the mathematical contribution of Camillo, but I'm not going to do that since most of you are aware of that. He is very well known about his contribution in geometrical measure theory, variational problem, Plateau problem. He has somehow worked on the heritage of the Giorgi, Federer, and Almgren, and his contribution there are absolutely outstanding. Camillo also worked in fluid dynamics and is one of the responsible of introducing these ideas of a convex integration already somehow used by Gromov in different framework, but they made this terrible efficient tool to solve really important conjecture in fluid dynamics. He also has done, that is part of young interest, so I like that he touched in non-irrelevant way conservation law. So what he has done, although it was not in the main focuses of his interest, what he has done is absolutely relevant even there. So my pleasure to introduce Camillo and enjoy the lecture.
Thank you very much. It's a pleasure to be here. Just one of many other times that I will be around. And yeah, so without further ado, let me enter into the topic of the talk, which is going to be about the boundary Plateau laws. So the Plateau laws actually are a classical concept which exists, in fact, in physics. But we will see what is the difference with what I'm actually going to present to you today. Okay, so first of all, this is what is called in the literature Plateau problem. So you're interested in taking a one-dimensional contour gamma in R3. So you can imagine your contour is a closed embedded curve in R3, smooth as much as you like. But this is not the only thing that you can actually do. I mean, you can take even more general sets. And now you're looking for the surface sigma of least area, which spans actually this contour. And you would see that much of the interest is going in understanding what kind of surface is sigma you actually should consider and what it means to span the contour. Okay, so this was actually posed, or it is attributed traditionally to the Belgian physicist Joseph Plateau, who was a physicist in the 19th century, so in the 1800s. And he actually proposed this particular variational model as a way to describe the shape of soap films. So what you have actually in the back of your mind, or what is like, the original interest of Plateau is the following. So you take a wire, which could be, plastic or metal, but somehow something rigid anyway, and you dip it in a bucket of soapy water. And you pull it out. And when you pull it out, the soapy water somehow makes a film, which attaches to the shape, a shape which attaches to the wire that you actually put inside. And I actually now don't remember anymore because, simulations and computer graphics are so efficient that this might actually be a computer-generated picture rather than something real, which was actually put in the bucket. So, in fact, even though it's named after Plateau, the concept of a surface that minimizes the area appears in the mathematical literature much earlier. In fact, as far as I know, the first time that it appears, it's in 1760 in a work by Lagrange, which is published when he was still relatively young and when he was still actually in Torino. And you can see that it's published in this journal over here, which is in fact the journal that he initiated as an editor when he became professor in Torino. So what does he do actually in 1760 in this paper? So he, in fact, introduces what is for us the modern calculus of variations. So he introduces this new method, that is what he calls actually nouvelle method, to determine maxima and minima of integral functionals. And it's exactly, the method per se is exactly how to derive the Euler-Lagrange equation for a minimum of a variational problem, which is minimizing the integral of some function which depends on, of some functional which depends on a function, okay? In fact, most of the work is dedicated to one-dimensional problems, and the minima surface problem, so the problem of minimizing area among all surfaces, appears in appendix. So exactly in the appendix, it considers the problem of minimizing the area among all two-dimensional graphs, so a special subclass of surfaces. This is actually the appendix. So, and as you see, he doesn't have our, like, sort of modern notation. So for him, see, p dx plus q dy is the differential of z, and you have to imagine z is a function of the two variables. So this gives you the height of the surface. So p and q are really the partial derivative in direction x and direction y of your function. And you see that here he has the integral functional, and the integral functional is exactly the integral in the two-dimensional domain of the square root of 1 plus modulus of gradient of f squared. So 1 plus the sum of the squares of the two partial derivatives. And that's exactly the total area of your graph. And you're trying to minimize this. And I mean, it's just like, if you actually read the green part, is what is saying something like, oh, by the way, we treated one-dimensional problems, but, if you want to have fun, actually the concept or like, the tools are general enough to treat actually even higher dimensional problems. And this is the example he picks. Okay, and you see that, he makes a derivation of the Euler-Lagrange equation, and he says something very interesting. So he's just saying these two differentials, of course, here you recognize the differential of the function, but here is the other differential. So these two differentials are exact. And, well, of course, what he means by exact is actually working locally. So for him, it's really like closed. So if you use differential forms and you compute what exactly he's saying, so this is what he's saying in modern language. So you actually find that the function z satisfies this partial differential equation. And so he derives what is called the minima surface equation, which is like the partial differential equation, which is satisfied by a smooth surface, which locally minimizes the area among all other surfaces, which coincide with this one outside of a compact subset. And it's probably, I'm not completely sure about it, but it's probably the first time that an elliptic partial differential equation is ever written in the literature. And it's quite remarkable because it's a nonlinear partial differential equation. So you would imagine maybe the Laplace equation was written before, but that does not seem to be the case. Although I'm not 100% sure because I'm not an historian of mathematics. Anyway, so let me go back to the Plateau laws. So what are the Plateau laws? So the laws that actually Plateau formulated in the 19th century. So roughly speaking, they say something like this. If you pick a point P, which is away from the wire that you have deep actually in soapy water, then in a sufficiently small neighborhood of this point, the soap film is going to be described by three types of different geometries. So it could actually be a smooth surface, as in the case of Lagrange. And then, of course, it would satisfy the partial differential equation that we saw if you write locally the surface as a graph. It could actually be that it consists of three smooth surfaces, which are coming together at a smooth line, forming degrees of 120, forming angles of 120 degrees. So locally at each point, if you see the angles at which, like, the three surfaces are coming, they are all the same. And then, It could be a smooth deformation of the cone over the one skeleton of a tetrahedron, okay? But a smooth deformation of a particular type. So the smooth deformation is not going to change the angles that the various pieces of the surface or the various smooth pieces of the surfaces actually form when they meet each other, okay? So I'm going to give you a picture. So this is, of course, the first possibility. You just look like a deformation of a plane, so you're a smooth surface. Or you look like a deformation of three half planes which are coming together at a common line by forming 120 degrees. This is what we will often call a triple junction. Or you might look like the cone over a tetrahedron. So like, you know, this one is the one-dimensional shape of the tetrahedron. There's the barycenter of the tetrahedron in the middle. And you're first connecting the vertices of the one-dimensional skeleton with the center. And these are like, you know, these kind of dashed dotted lines. And then you see for every three lines that you formed, which form a triangle, for instance, this one is the one-dimensional, one edge of the one-dimensional skeleton, and these are like, you know, two which are connected with the center, the two vertices of that edge. Then you fill that one with a triangle, okay? So there are 6 triangles which are coming together. They meet with a common point at the center. And then, of course, each 3 of them is forming a triple junction on these lines over here, okay? Very good. So this is actually a mathematical theorem in the following sense. So first of all, you have to assume that as a physicist, Plateau was correct. If you actually look at soap films, and you really look with a microscope at what is happening, you will discover, of course, that a soap film is not a surface. It actually has a little thickness inside. But in fact, when you actually do experiments, you can see the water moving inside this kind of like, you know, little chamber. So the soap film is really a capillarity problem. And so it's a problem that has a thickness. It's described by a surface with 0 thickness, only in some physical limit. But if you accept that minimizing the area of surfaces is a good model for the soap film, then you can actually transform the Plateau laws into a mathematical theorem on area minimizing surfaces. And this is what actually Gene Taylor does in the 70s. So here it is the way the theorem is formulated. So you take a 2-dimensional set in R3, okay? And you want to give a concept of what is a set which is minimizing area, okay? And this is the concept. So you are allowed to deform your set E with any Lipschitz deformation, which of course is going to be the identity outside of a compact set, right? In such a way that, you know, you're only deforming like your surface locally. Now, you cannot take any Lipschitz deformation. Your Lipschitz deformation has to satisfy 2 properties. It does not move gamma, so it keeps gamma fixed. And in fact, it's also doing something more stringent than keeping gamma fixed. It really keeps a neighborhood of gamma completely fixed, okay? So the phi is the identity in a neighborhood of your boundary, of your wire. And the other thing that you cannot do, according to this model, you cannot take a piece which is like, you know, a portion of the region which is outside of gamma and make it like, you know, bump into gamma. So like, you know, passing across it. And so this is a bit more complicated to write in formulas, but it means the following. If you look at, if you look at the points which are not moved by phi, if you look at the points which are moved by phi, which avoid the neighborhood of gamma, so you look at where these points might be mapped, and none of these points can actually be mapped on gamma. In fact, you also require that the closure of this set does not meet gamma. So you're always at some positive distance from gamma, okay, with this deformation. Okay, now why would you actually take this particular concept of being a minimizer, right? Well, there's like, you know, one of the things that you have to model, and here is where, you know, we could debate a lot, is what it means for a closed set to have gamma as a boundary, okay? One first thing that I could do is I could tell you, well, the heck with it, right? I mean, restrict yourself to smooth surfaces, which have the boundary gamma just in the sense of differential topology. So a smooth-oriented surface with boundary gamma. Unfortunately, if you do that, and you minimize the area among all surfaces with that property, the minimizer is going to be a smooth minimizer. So you will never see the geometry 2 and 3 of the Plateau laws. You will always see only the geometry 1, which is an experimentally wrong thing. I mean, sometimes you dip things in soapy water, you take it out, and there's a triple junction forming, or there is a tetrahedral singularity. So that model is not good. So you have to take more general surfaces, and for more general surfaces, you have to understand what it means for gamma to be bounded by this surface. And there's various concepts in the world. So there's Reifenberg, Harrison, David. And for all of them, one thing that you could actually ask yourself is, how does nature, understands that that one has to be the boundary? And it's tricky, because if you take, for instance, Reifenberg's solution, the concept of spanning the boundary is that the Čech homology of gamma inside E has to be trivial. And so, if you have our time believing that God plays dice with the universe, you could actually wonder if God computes Čech homology of a set. Of course, what is really happening is that the way you're dipping the water, the way you're dipping the thing inside and then you're taking it outside is a dynamical situation in which the film is slowly kind of forming. And so it attaches to a substratum, which is actually the water in the bucket. And then it's forming some solution in the end. And it's kind of not obvious the way it understands why it has attached to the boundary. And in fact, if you want to try to study the problem really from the physical point of view, as a mathematical physicist, what you should do, you should actually look at the free energy on the space of surfaces with a thickness, so really at the capillarity problem, and then try to understand what happens where the capillarity goes to 0. And this, in fact, has been attempted in the literature, and there are quite beautiful papers by Maggi, Stuvard, and collaborators. But anyway, what is kind of nice is that all of these different models, all of these different treatments, when you actually get into the limit, or when you just take the definition of Reifenberg or Harrison or David, you actually end up with a class of surfaces which minimize for sure in the class of Almgren. So in some sense, if you're proving a theorem for minimizers in the sense of Almgren, you're proving a universal theorem, because it's kind of the weakest notion for being a minimizer that you can find, which still allows for the formation of singularity. Because, of course, I could take the notion with kind of classical surfaces, and then I would never see singularities. Okay, so this is Taylor's theorem. So Taylor's theorem actually tells you the following. If E is an Almgren minimizing set with respect to a boundary gamma, and P is not in the boundary, then it's a sufficiently small ball. The set E is diffeomorphic to one of the 3 models in the Plateau laws. So, and this is the only possibility. So now here is the problem that I want to pose and address in this talk. So what happens if you are at the boundary? So if P is actually in gamma, what are the possible geometry that the soap film is going to do? Or if you want to abstract on the mathematical problem, if P is in gamma and you take an Almgren minimizing set, what are the possible shapes that this Almgren minimizing set can actually have at the point P, in the neighborhood of P? And so you would aim for an analog of the theorem of Taylor, which actually does not exist in the literature. And to my amazement, it does not seem even to have been kind of, guessed or conjectured on the physical literature. Okay, so we're going to make some assumptions. So first of all, even though I will show you experiments with kind of shapes which are more complicated, the first thing I want to understand is what happens when I have actually a sample gamma, which is a regular curve. Or maybe you can take a sample gamma or a wire, which is not a regular curve, but I'm going to only look at the geometry at the point P on which my curve is regular. Okay, I have to start somewhere. And that is already an interesting problem. So at the point P, where gamma is regular, you have, of course, a tangent line. And there's a general fact, there's a general theorem, which tells you the following. It's a very powerful because it works in utter generality, but it works in particular for the Hamilton minimizing sets. If you put yourself at this point P, and you take a small ball, right, and you apply a rescaling, so an homotity, so to make the small ball a ball of radius 1, then as you rescale and you rescale, your surface has the tendency to look more and more like a cone. I mean, if you remember the theorem of Taylor, all of these shapes that we actually saw are conical with respect to a central point, right? I mean, for instance, the tetrahedron, which is the least symmetric, is conical with respect to the central point. And that point is really the point P that you were focusing on in the theorem of Taylor. So already in the theorem of Taylor, you actually conclude that in a sufficiently small ball, you're going to be a deformation of a cone, which is centered at that particular point P. This is true even at the boundary. It's a consequence of the so-called Allard monotonicity formula at the boundary. And mathematically, what it says is the following. If you take your set E, you rescale, I mean, you first translate in such a way that you put yourself at the point P. This is what you're doing. So P now becomes the origin. And then you make an homotheties of ratio 1 over Rk. So you pick a sequence of radii, which is going to 0, and you rescale these radii to 1. Okay, now you see the rescaled surfaces, and the rescaled surfaces are converging in a very precise sense. In particular, they are converging in the sense of Hausdorff as locally compact sets, but actually even in a stronger sense than that. They are converging to an Almgren minimizing cone. So to a conical shape, which is now going to be minimizing with respect to the boundary, and the boundary has become this tangent line, right? I mean, because when you are rescaling, you're seeing more and more of this gamma, which is flattening, and the complicated topology is actually going to infinity. And so the problem that I want to pose is, in first approximation, can you classify the cones which are area minimizing locally in the sense of Almgren, and which have a boundary which is a straight line, which is going through the origin, okay? Now, here's the problem, as I said it. So classify all closed sets E in R3 with the property that they are a cone with respect to the origin, so they are invariant under rescalings. This is the first condition. Well, of course, you want that the cone has locally bounded area, right? Because if it has area infinity, then being a minimizer doesn't seem to make much sense. It's anyway a property that you get for free when you're doing these rescalings, exactly because of the monotonicity formula. And then you want to be Almgren minimizing with respect to the boundary L, which is a line through the origin, okay? Now, observe that just given this data, there are three possibilities for the boundary line. So either it intersects the set E in the origin, or it intersects the set E in a half line, or it's contained inside the set E. Now, you might ask whether the two situations are actually relevant for soap films. And to your amazement, I actually tell you right away, it might be relevant because sometimes, even if you're like, dipping a wire and taking it out, the soap film does not attach to the whole wire. In fact, it doesn't wet the whole wire. It's not something that happens often. I mean, if you actually put a reasonable curve and you put it, and you take it outside, it attaches to the whole sample, but not always. I mean, you can see actually experiments in which it does not do that. Why? Who knows? Maybe because the dynamics with which you actually did that is a little bit strange, or maybe because, I don't know, the curve makes a very complicated topology. I don't have an explanation for that. I will, in fact, focus on the first case, which is anyway the most prevalent situation. And it's the case in which you would, like, physically say your film wets all your boundary, okay? And so here's the theorem, which, as you can see, it has a hopefully 2025. It might be dangerous, actually. I think we got all of the details covered, but we're still writing some details down. Hopefully, there are not going to be any surprises. But anyway, So the theorem would say the following. If you have an unminimizing cone with respect to a line L, and you assume that L is inside E, so the first or maybe the third of the three cases, then there are exactly 6 possible geometries that you can see at the boundary. So note that it's not an if and only if. So we know for a fact that 4 of these geometries are minimizing. The other 2, they look minimizing. I will show you experiments that actually show that. But we cannot prove that they are minimizing. I mean, what we can prove is if you are a minimizer, then you have to belong to this list of 6. But it might well be that the list is actually shorter because maybe we are wrong. So these are the 3 simplest geometry that you can have. So see, here is a film which simply stops at the boundary. That's what you would expect in most of the situations. This is a film which arrives at the boundary with 2 different planes. Now, if you arrive with 2 different planes, this angle which is formed, the convex angle, has to be between 2 pi over 3 and pi. So it can become larger and larger until it becomes flat, but it cannot become too small. It cannot go actually below 2 pi over 3. Then there's, of course, the triple junction, in which the wire is passing exactly in the middle of the triple junction. And all of the 3 planes, they're actually coming there at 120 degrees. I mean, of course, you can imagine if this was minimizing in the interior, well, it's minimizing also with the boundary, right? I mean, because it's minimizing even if I move actually this core. In particular, it's minimizing if I don't allow you to move the core. And these are all minimizing. What is the 4th geometry? It's again not a surprising geometry. So if you take 2 edges of a tetrahedron and you take the 2 edges which don't have a vertex in common. So for every edge, there's exactly another one that doesn't have a vertex in common with it. And if you take the midpoints of these 2 edges, the line through the midpoints is actually contained in the cone because it's passing through the origin. So this is also, and there's no other lines. So these are the only lines which actually exist in the tetrahedron. So this is minimizing in the interior, of course, the tetrahedron because of Taylor's theorem. Then it's minimizing in the boundary too. Now, here's something which is not minimizing in the interior, but it seems to become minimizing at the boundary. So now take a cube. A cube is symmetric with respect to the origin, so it contains a lot of lines. Now, if you pick, I mean, there are 2 possibilities. You pick a line which is going exactly through 2 vertices of the cube, and that actually in experiments look minimizing. And then you can like shift this line and move it until the other extremal situation, the line which is going through 2 midpoints of 2 opposite edges. Well, if you put the line joining 2 midpoints of 2 opposite edges, we can prove it's not a minimizer. And if you actually are with the line which is passing through the 2 vertices, it does look it is a minimizer. And so you would conjecture that somewhere in between there's a phase transition. So there's a point at which you move the red line, you're still minimizing, then at a certain particular point, you're still minimizing that you can prove. And then as soon as you shift, you become non-minimizing, okay? But this is not something we can prove. This is something we conjecture. And then, and this is something that we have never seen before in the literature. So here's actually an experiment. So you can probably not see it very well, but you see there's a little line over here, which is a very little string. So you see the boundary, I got it 3D printed and it's kind of like, thick. But I want to insist that, the central point might be delicate. So I don't want a boundary which has too much thickness compared to the, width of the film, which is very small. So I've taken a very small string, which is red, so you should be able to see it, but it's this string over here. And it's not exactly going through the vertices, it's a little bit off, okay? But you see that it seems to be forming a cone. Now, of course, you see is a little bit tricky. I mean, you might wonder what happens if I zoom and if I actually look at that point, it seems very small. So I tried to do that. I mean, you can do it in the picture. I cannot do it on the slide. Okay, now there's another geometry, and this one was, so this is a funny story. I will tell you, during the proof. So this is actually something we came up with pen and paper. Like, when we were trying to classify, at a certain point, I was trying to prove that something doesn't happen. And after trying to prove that something doesn't happen, I realized that for a week, I was actually trying to disprove something that does happen. And I wrote down an explicit stationary cone, which has this shape. So in this shape, you see there are 4 points. Those 4 points, they are the 4 points of a cube inscribed in a ball of radius 1. I'm not drawing the edges actually curved. I'm drawing them straight simply because it's easier for you to look at. At least my collaborator, Federico, tells me if I had a picture in which it was curved, and he told me, nobody's going to understand that. It does not really matter that I actually do the things straight. If you're a cone, when I actually put the straight line, it's passing through the cone. So if you don't see a minimizer, which is a cone for that sample, you're not going to see a minimizer, which is a cone for the sample in which I actually put the curves or the arcs on the sphere. Okay, then you see that there is this long equator, which is joining the other 2 points by going the other way around the sphere. And so the soap film will actually put soapy water over here. And then you see from here, I'm actually drawing a piece of the equator, which is passing through the points V2 and V4. And I'm going through this equator until I hit a point P1, and then below until I hit actually a point P2, which is opposite to it. Now I have a degree of freedom, as you see, right? I mean, I could actually make this gamma 6 much shorter and this gamma 7 much longer. I could actually go as far as making P1 coincide with V2 and then make gamma 7 as longer as possible. And these are all possible shapes in this family of cones, and they all look minimizing. So here's one guy. So you see, this is an extreme example because one of the two arcs over here has become like negligible. So this would be this arc gamma 7, which is actually going to become 0 in length. There are more experiments. Some more experiments. Maybe here you see really very well, like, the string. And then I have a very trusted collaborator who's actually doing the experiment live. Very seriously also. Yeah, I mean, you see the 4, the 4 triangles which are starting with the cube, which are getting actually at the central line. And really, this is a very robust experiment, meaning that in many other situations, the cone is not that stable. So there's me really going slowly. But I mean, my son is just going, boop, boop. And it still forms a cone. Okay, so now, I mean, there's 20, 25 minutes. Let me tell you something about the proof. So the proof is actually kind of a tour de force. There's 100 pages, projected 100 pages of theoretical pure math part. And there's a lot of hard computations which are actually done on a computer. So it's a computer-assisted proof. I will try to show you how we can use the computer to do certain things. And I mean, certain things will be obvious that you can do on a computer because they are discretized in nature. Certain other things will be less obvious. But so the combination of the code and the computer computations and the theory should give a complete proof of the statement. It's a fairly long computer code. I mean, we have actually to make several programs to make several different parts. Okay, it was a lot of fun because we ended up using tools in so many areas of different areas of mathematics, which I could hardly believe it myself. So, of course, you know, we're talking about two-dimensional cones. So it's very natural to intersect your cone with the spherical, you know, with the sphere of radius 1. And so look at the link of the cone. And you might, of course, suspect, if you know a little bit of calculus of variations, this will be completely obvious to you. But if you looked at the picture, you might also suspect it. When I intersect my minimal cone with the sphere, I find a one-dimensional set, which consists of geodesic arcs, which are joining at the points. The special point, which are fixed to you by the boundary, because your line is intersecting the sphere into two antipodes. And then other points, which are points corresponding to triple junctions in the interior, as you might have seen actually from the pictures, right? I mean, in the pictures, there were a lot of triple junctions, which are actually getting out of the central point. And, you know, when you sort of go back and you go to the sphere, you will see triple junctions on the sphere, right? I mean, see, these things over here are all triple junctions. And beware, I mean, like, you know, this triple junction over here is really where the boundary line lies, where there is my very subtle string. But you see, these triple junctions over here, they are not forced by any string. There's no string actually there connecting to the center. This is really the minima surface itself, which is making the triple junctions of Jean-Taylor in the inside. So there's obviously spherical geometry because, you know, I'm having geodesics on the sphere. Now, also not surprisingly, there's graph theory because, you know, the topology of what you actually find on the sphere is a graph, is a one-dimensional graph. It consists of points which are connected by edges. There's Lie group theory. So, and I will show you why actually Lie group enters, and you know, because there are isometry of the spheres. And one of the ways of parameterizing isometries of the spheres, which is very effective, is to use the units of the quaternions to transform problems on the composition of isometries of the spheres into algebraic problems in multiplications of quaternions, which is quite useful. Not so clear, we actually needed to use some computational algebra tool, in particular Gröbner basis. This will be clarified also a little bit further on. Also really not clear, and this was a very, very big surprise at the end, we actually need to use some serious low-dimensional topology. In fact, low-dimensional topology of two-dimensional simplicial complexes. And if you are naive like me, which has happened, I mean, like, you know, I called a Zoom call with one of my friends who are actually an expert in low-dimensional topology. And I told him, I have a very simple problem. You know, I have a two-dimensional simplicial complex. I mean, you must know everything about it. And then he tells me, like, you know, it's as complicated as three-dimensional manifolds. I was like, no, wait, it's a two-dimensional object. And then he tells me, yeah, it's a two-dimensional object, but it's not a two-dimensional manifold. I mean, if you think of triangulating a three-dimensional manifold and put yourself in each cell of the triangulation and take away a point, you can actually homotopize the manifold without the points on your two-dimensional simplicial complex. And so that guy is topologically as complicated, typically, as your three-dimensional manifold. And of course, a lot of geometric measure theory. Okay, so, and we face computational challenges, in particular because you will see the things are quite complex. At a certain point, there was an estimate in which one constant was not really optimal, and the computer was taking, like, you know, 2 weeks without ending the program that was supposed to do something. Okay, so let me make the first theoretical consideration. I already did part of it. So Taylor's theorem implies the following. If you take your cone and you intersect it with the sphere, you get a geodesic net. So a one-dimensional set, which is the union of the geodesic segments. And what are these geodesic segments doing? So they're pairwise disjoint. They meet at some common vertices, which are the endpoints of the edges. There are two special points, which we are going to call P and minus P. So these are the intersection of your line with those 2 points. And, well, it's something that you can prove that the degree of that point, so the number of edges which can actually get at that point, is either 1 or 2 or 3. If there's 1 point arriving to it, you don't have any condition. If there are 2 points, they have to form an angle which is at least 120 degrees. I mean, you saw this claimed in the theorem, but it's something that you can prove a priori. And if there are 3 which are arriving, they arrive like in a triple junction, so they form 120 degrees. Okay, then there are other vertices. So the other vertices are somehow the free points, and at those free points, those are not free because they're in intersection with the boundary line, so you can't move it in your cone. So at those other points, you always have 3 edges which are arriving and which are forming equal angles. Okay, so now at this point, you look at it and you could say like, oh, wow, okay, this looks like a geodesic net, which is pretty rigid after all. So how many of them there possibly be? You actually saw 6 of them, right? Because those 6 minimizers were producing nets of this type. But one way you could actually understand the problem of classifying all the cones would be, okay, I solve the problem of finding all of these geodesic nets. They're going to be, I don't know, maybe 10. And then 6 are the minimizers. And for the other 4, I'm going to produce a counterexample to minimality. So I'm going to produce a surface which has less area and which has the same boundary. Now, that's very beautiful. It's in fact what Taylor does in the first part of her paper. But there's a catch. There was a beautiful paper by a Hungarian mathematician in the 50s. His name was Hepes. He actually died kind of recently. And he classified when there are no special points P and minus P, so when all the points are free, he classified all of the geodesic nets which have only triple junctions on the sphere. And there's not that many of them. There's 9. It's a beautiful work. There's a problem. He uses very clever inequalities and very nice symmetry considerations, but because we have these 2 special points, P and minus P, you see the symmetry is somewhat broken over there. So for him, any vertex looks exactly the same way because there's always 3 guys coming and they always form 120 degrees. You already see that for us, it's more complicated because not only at these special points, there might be 1, 2, or 3 edges. But if there are 2 edges, they're free of forming an angle which varies continuously between 2 pi over 3 and pi. So you might imagine we certainly don't have his rigidity. In fact, each of his examples is rigid up to isometries, but you saw already in our theorem that there's one example that for us is not rigid, right? I mean, because if you remember the final example, there was this uncertainty on how long are the 2 edges which are connecting to P and minus P. Okay, that was a 1-parameter family of non-isometric possibilities. And in fact, in our cases, there are 30 distinct topological types. And some of them are nasty. So many of them come as a 1-parameter family, and there's one family that comes with 2 free parameters. So it's really a large, sufficiently large moduli spaces. And we found around 20-something of them with pen and paper in the span of several months of considerations. And I was convinced they were them all. And then it was actually the computer producing some 10-ish other, which we didn't see with pen and paper. Okay, so where are the graphs coming? Well, so there's something that you can actually do with the theory, which is if you make some simple considerations using spherical geometry and Gauss-Bonnet, one thing that you can immediately say, which is very optimistic, is that the topology of your graph is finite. So there's only a finite number of possibilities for the topology of your graph. this is not so difficult to believe. I mean, for instance, if you have a spherical polygon, which has only angles of 120 degrees inside, that polygon can only be a biangle, a triangle, a quadrilateral, or a pentagon. It cannot be an hexagon. So that already tells you convex faces cannot have more than 5 edges, which is a pretty big help. Because on the other hand, by Gauss-Bonnet, if I give you a pentagon with angles of 120 degrees, you can find that the area of that pentagon is 1/12 the total area of the sphere. So you cannot have more than 12 of those pentagons. Okay, on the other hand, if you want to try by these kind of considerations to narrow down the list, which is finite, and you want to do it by hands, at least given the initial number of conditions, you're going to run crazy, because we programmed the computer to do that and to produce a possible list of topologies. And the list has a bit more than 3,000 elements. In fact, the initial list had 6,000 elements. Before, after like, I don't know, a month, we noticed that there was, 2 guys that looked exactly the same. And we just noticed that we forgot to apply the mirror symmetry, which is of course mapping an area minimizing cone into itself. So we were only using orientation preserving symmetries. Okay, now at this point, you can fight with some more theory. So you can try to apply more sophisticated kind of spherical geometry arguments. And you can write down pen and paper restrictions for these topologies, and you can actually narrow down the list to kind of 500-ish cases. And then you start hitting like, nets which seem to be too complicated to actually carry over some elementary considerations in spherical geometry. Okay, so nonetheless, the first part we certainly apply. We actually have very long lemmas and proofs that something cannot happen. And finally, for the part I'm going to tell you, whether you're left with like 500 cases or 700 or 800, it doesn't make a big difference. So in the paper, we are not really using all the theory that we developed over here, but only a subset. So anyway, you can look at the list. And because the computer can handle actually finite topology, you can exactly tell to the computer what your lemmas are excluding. And so you can actually reduce your list. And then at that point, you're actually finally with some hard situations. And here we start applying some more ideas. So first of all, there's more spherical geometry, which is a quantification of Hepes inequalities. So this was something which I was told only later by another Hungarian combinatorialist. So actually, when Hepes produced the paper, it was refereed on Matzainet by Coxeter. And, Hepes' paper is quite beautiful and elegant. It's like, 10, 11 pages proof. But Coxeter, in the review, gives a proof. In the review, which is a paragraph. Because he can actually reduce it to some known things for polyhedra. And so, it looks kind of bad, but we were extremely lucky that actually Hepes published this proof. Because with Coxeter proof, we wouldn't be able to do anything. But with Hepes proof, what we can actually do is we can take some of the inequalities that we actually uses and make them more quantitative. And that one helps us in trying to build a computer algorithm which excludes the existence of nets, of stationary geodesic nets with that topology. So those inequalities are very good for convex faces, but they're not so good for some of the faces which are not going to be convex. And remember, because we have these points, with edges which are coming together, only 2 of them, there will be some faces which are not convex on the sphere. And in fact, to tell you the truth, we do something which at the beginning looks silly. So the special points, the 2p and minus p, we actually remove them. And the reason why we removed them is because then the net which is left has only angles which have 120 degrees, which makes you hope that it is going maybe to be rigid. And in fact, it's rigid. That one net, like what we call the derivation of the previous net, is rigid in all but one family. Anyway, now you have a non-convex face. And you ask yourself in which way you actually can write down the condition that this polygon is going to close itself by forming angles which are like 120 degrees. And you realize you can do the following. So you can just say like, okay, let me be an ant. So an ant is starting on the edge, goes up until here, rotates, goes up until there, rotates. And you can imagine that attached to the path of the ant, you can actually attach an isometry of the sphere, right? I mean, the ant is rotating, but for the ant, maybe it's exactly the same as if the Earth is rotating under it, right? Then it arrives at a certain point and the ant is turning, but it is exactly the same as if the sphere is turning on the ant. Now, what happens at the end of the whole procedure, if you actually got back at the initial point, and if you got back at the initial point with an angle that you know, at the end of all the composition of all these isometries, you actually got the identity. So because you can split your isometry in finitely many cases, so you're applying a path from here to here, then a rotation, then a path, then a rotation, and you can write explicitly what are like the isometries. And because you can parameterize the isometries with quaternions, you actually describe that there is a quaternionic identity attached to each polygon, which tells you the multiplication of these quaternions, which I can explicitly compute, goes back to 1. So being closed is equivalent to a system of algebraic equations, which you can write on quaternions, which is the product of certain special quaternions has to be equal to 1. So you find an exact identity for being a closed loop. Okay, this actually makes you think, and it gives you a sort of blueprint of why you can do stuff. So you can write down your condition of being this geodesic net as, if you look at the length of the edges, so the topology is fixed. So you know that you have, 17 edges, which have a certain topological structure. So you know which ones are the edges. Now, the fact that you're able to arrange the length of the edges in such a way that all of the angles are 120 degrees and then you close the polygons and so on, is equivalent to an awful system of algebraic equations on sines and cosines of your length. Like, maybe 12 equations. And it's a system of polynomials with integer coefficient. So actually your set of solutions, when expressed in cosines of the length of the edges, it's a real algebraic subvariety of some huge space. So if you actually make some parameter counting, you realize that you are slightly overdetermined. So in the case of Hepes, actually he has 3 equations more than unknowns. And so it's kind of rare to find a solution. A solution really happens because certain symmetries are making certain equations redundant. And then at a certain point, you actually go down and you find a situation which is rigid. It has exactly as many equations as unknowns. In our case, because of the 2 special points, we have 1 equation more than the unknowns. And so that's why actually there's many more solutions. Now, you would be extremely happy at this point because you say like, oh, but my problem is now completely determined. Yes, except the degree of your algebraic variety is maybe 1 million or so. So you can't actually use hard tools from algebra to solve it. But in certain simplified situations, and we actually make use of this, when we are not smart enough to use spherical geometry to prove, for instance, that the net has a certain symmetry, we can use heavy algebra to actually translate it into an algebraic problem and then prove the symmetry by brute force, by using Gröbner basis. And this is what I actually said at the beginning. Okay, anyway, so you can package all of these theoretical parts and you can now produce a computer algorithm which takes the following inputs. It takes a topological graph. And it takes a tolerance, delta, so a number, which, in our actual implementation of the algorithm is 1 over a million, 1 over 100,000, so 0.00001. And the algorithm is telling you the following. Maybe there's an output, and the output is there is no possible geometric realization of your topology. So your topology does not sustain a stationary net, so for sure not a minimizer. Or it could tell you it is possible, and if it is possible, it's going to give you a list of numbers which are the length of the edges, and it's guaranteeing you that it makes an error in the nth of the edges, which is no more than delta. So, of course, here's the tricky part. If I put delta to be like, 1 over a billion, the computer is not finishing in 1,000 years. So, at least not on the laptop. I don't know. Maybe in a year on a big cluster. Anyway, there are 2 further key ingredients from pen and paper theory. So, we don't really classify all of the stationary nets. We classify the stationary nets for which the edges are bigger than something like 0.05. But we can use the minimizing property to show that the edges have to have positive length. The stationarity condition wouldn't tell you that. And then, there's a hard estimate on the propagational errors in the composition of isometries. This estimate was botched. I told you it was the estimate with a botched factor of 10 on the constant. The constant is actually equal to 1, and it's optimal in the paper now. And because this estimate is optimal, actually the computer is much faster. Okay, now you've got your list of roughly 30 candidates. And the pen and paper classification of some cases, which we actually do, so we don't do everything with the computer. In particular, we try to do the flexible ones in pen and paper. Because you see, the computer is pretty good at telling you what the numbers are if there's no freedom, if there's no flexibility. But if there is a flexibility and it has to tell you all possible edge length, then it has to give you a 1-parameter family of them, but discretized by this delta. So then it's going to give you like 10 to the minus 5 of them. And that is not good, right? I mean, it's something that is unwieldy. Okay, now in the remaining cases, you actually want to show that there's a competitor, right? Okay, so this maybe I said it before. In a couple of cases, we guess a certain symmetry, but we're not able to prove it with elementary considerations in spherical geometry, so we need algebra. So now what do we do at the very end? So there's something which is called Braque surface evolver, which is a wonderful piece of software. So what this Braque surface evolver does, you input a surface and you can evolve it by mean curvature flow. Now, of course, we're talking about stationary cones. So what we actually do is we input these stationary cones in Braque surface evolver. We perturb them a little bit, we destabilize them, and then we let actually the evolver flow. And the evolver, more often than not, is producing a surface with less area, which has the same boundary. And then you've actually produced a competitor and you're finished. Now, except not so fast. So there's certain subtleties. So the first subtlety is that we don't exactly know the edge length of the net. But you see, it's a variational problem. So if I have a good enough competitor for one guy, and I know that the other guy is nearby, I can actually use the theory to bridge the 2 competitors together without losing more than what I gain. And so theory actually settles that. But there's another big problem. Braque actually has bugs. If the code were doing all that he claims to do, then you would be sure that you have a proof, but it might not be doing, and sometimes you see that it's actually making errors. I mean, it's unclear if they are numerical errors, if it's an implementation error, it's unclear, but it's a very big code. So, but what does guarantee us then that the computer that the competitor satisfies the boundary condition? Actually, Braque gives an output, which is a triangulated surface. So which means it gives actually a simplicial complex and the map of the simplicial complex on the sphere. And so your surface is a union of triangles, and now you have to check whether that particular topological surface or topological object actually takes the boundary condition. And this is done by a code which we write separately. But pay attention, Hundreds minimality, in fact, requires the construction of a map, whereas bracket just gives a set. So to pass from the set to the map, we actually have to do some non-trivial topology. Okay, so let me just make some acknowledgements and then I'm finished. The research has been supported by a grant of the Simons Foundation. The 3D models actually have been printed by two very kind engineers from the University of Passau who are specialized in printing models, and they've printed like 70 or 80 of them for me. And there have been several discussions with some people, Guy David, Jonas Isch, and Simone Steinbrüchel, who were fundamental for this project. And that's all I want to tell you.
Yes.
Thanks for a very interesting talk. I have actually two questions. The first, what about the stability of each surface? So is it possible to understand by topology or by algebraic properties the stability?
Right. So it's an absolute, okay, so the ones which we conjecture are minimizers are an absolute minimizer. So those ones, they should be completely stable under any kind of perturbation. Now, so stability is a little bit tricky, depends on how, even for the stationary ones, if you want to create a competitor, you have somehow to kind of modify the topology. So you're not acting via diffeomorphisms, but you're really kind of for instance, taking maybe two faces and identifying them, splashing them together, because that actually makes you gain area. Now, if you allow me that type of deformations, stability and minimality is the same, because what I could do is the following. So you give me your competitor, which is a competitor for a cone. So I take your competitor and I homotetize it in a very small ball. I put your competitor just on that small ball, because after all, that is a cone. So I cut out only this ball of reduced epsilon. And then I inflate your competitor back by making kind of, shrinking the cone back. And so I can always find a one parameter family of deformations from one guy to the other, which is always strictly going down in energy. So in that sense, you could say we're classifying not only the minimizers, but only the stable ones, because of the conical shape, the stable and minimizer is essentially the same. But we don't see a way of taking advantage of this kind of in a classical calculus of variation sense. I compute the second variation and then I get an inequality and wow, I'm going to exclude actually many of them. And the reason why we don't see this is possibly because we have to change the topology. So it's not easy to compute the second variation because the space of deformations is not that nice after all.
Thank you. Another question. So there are some obvious relations to Steiner nets, of course. Yes. So these results in particular include Steiner nets in
Yes.
Special cases.
Yes.
Is there any kind of analog of Gilbert-Pollock conjecture for this case? So if you prohibit any junctions, then we lose not much in the minimal area, like that, something like that.
So you prohibit any triple points?
Yes. So if we have let's say if we have several curves, several smooth curves, then the minimal possible area of a surface, which in some sense cover all these curves. So if we consider the minimal possible surface, and if we consider the surface which is piecewise smooth on and the loss of smoothness can be only on these curves. So the second case is not much worse than the first one, like that. Yeah, like in the Gilbert-Pollock conjecture.
Like taking everything completely smooth.
Yeah.
No, I would say, in this case, it makes a difference, because if I minimize in the, say, space of smooth surfaces, of smooth oriented surface, my minimizer in the interior is always going to be completely smooth. It doesn't see the triple junctions. And so I really see a Lavrentiev gap between the two problems. So if I minimize in the space of smooth, say, surfaces, I will see a completely nice smooth surface. And it's going to have strictly larger area than the ones with singularities. So no, I mean, the singularities are kind of important.
Yeah, thank you.
Yeah.
Other questions? Or just a generic question that you have several tools where you somehow create more complexity in the problem because you clearly have, for instance, when you pass to spherical geometry, you have very big systems. But what is the real point that you can somehow reduce the complexity? Which kind of this argument is the one that plays the role? Because at the end you have not around that. What is essential to do that?
So what is essential to do that? So let me tell you the most important input from spherical geometry. I mean, it's not the most important input in the sense of the proof, but I think it's the one which is going to give you most of the rigidity.
Yeah.
So, I mean, there are these special points in which you don't have, assume I remove them so that everything else has 120 degrees. Okay, then if I remove them, I have maybe 4 special points at most. But at least in there, my angles are always 120 degrees. Okay, now if you notice, you take the complement of the sphere and you ask yourself, well, sometimes I'm going to see the complement of, a point of degree 2, which is forming a 120 degree angle over here, and on the complement is forming a 240. So how many of those faces there are? There are actually at most 2 concave non-convex faces. Everything else is convex. So now being convex at with 120 degrees forces you a lot of rigidity. For instance, if you see a face which is a triangle, that triangle is the triangle of the spherical tetrahedron. It's completely determined. And then it's completely determined, and you just say oh, okay, I just have 3 edges which are completely fixed. It kind of essentially gives you all of the other edges by some more spherical geometry considerations. So if you have a quadrilateral has 1 degree of freedom. So essentially it can become narrower and narrower until it's not too narrow. I mean, it converges to a biangle, or on the opposite, it can become as symmetric as the square of a spherical cube. So you have a 1-parameter family. And now there's, unfortunately, the nasty ones, which are the pentagons, and the pentagons actually have a 2-parameter family. And those ones, so the more pentagon you have among the convex faces, the harder is your problem. On the other hand, the proof of Eppes gives you certain inequalities between these edges. And what actually the computer program is doing, I mean, the one that really kind of makes us pass from, 500 or 600 to 30, is essentially iterating these inequalities several times. And so if we didn't have if we were to feed to the computer program the original situation of Eppes, very quickly it would converge to the correct edges for the topologies which are possible. Because the iteration of these inequalities is restricting somehow the possible values of the edges further and further. Now, unfortunately, because we have also the 2 concave faces, we have many more situations. And so, I mean, the way the computer program is really working is, it cranks all of these inequalities very quickly. And then at a certain point, it tells you okay, the inequalities are not giving me any more constraints. Okay, then the computers, the program does the following. You take a few edges, which, by a parameter counted would determine everything else. You have an admissible interval of length for those 2 edges. It refines into 2 pieces. So then it bifurcates the graph, and it starts repeating these inequalities very strongly. And as long as you can actually take advantage of these inequalities, the algorithm goes super fast. And so unfortunately, I mean, like, you know, in the 30 situations, there are some symmetry of the sphere and of the net, which makes these inequalities kind of inefficient. And of course, it makes the inequality inefficient for a very good reason, because there are in fact many solutions maybe to your problem. But yeah, that input from spherical geometry is what, in the end, is the kind of, you know, the one which makes the computation feasible, if you want. Then, okay, with that one alone, you wouldn't be able to complete the proof anyhow.
No, because then you need to reduce.
Because you need to, yes, you need to understand further what happens, like, you know, when these are not so powerful. But say, just by running these inequalities, maybe you drop from, I don't know, 500, 600 cases, maybe to 70, which are harder.
Yeah.
Yes.
I have just a very naive question. I mean, you have somehow, you put somehow this, you had this red string, which somehow gave you the boundary. What is actually if you go only, make a boundary which only go half the way? I mean, so that you will get only on the sphere, only one of the 2 points. Would that be better or worse?
So you want to kind of not connect P and minus P.
Exactly.
You want to just like go, for instance, from here to the center.
Yes, because then you have less restrictions on the sphere at the end, no?
All right. Okay, so this would correspond to the, okay, and then you don't have that point P. At that point P, you would have the triple junctions. Yes. So when I actually explained to you the, you know, the 3 cases, that's exactly why we started with, I mean, if you, when was this? It was when I actually stated the theorem. Yes, no. Here. So you're bothering about this situation. So I know it's a cone, so I know the intersection of L has to be either a line or a half line or the 0. Yes, so this one would be expected to be easier. So that is like, you know, these 2 cases is what we want to do in the next, I don't know, 6 months, maybe after we have closed this guy. I mean, possibly this one is not going to be any surprise. It intersects, you know, you cannot move the central point, right? Because the central point is fixed, but possibly you only end up with the examples of Taylor. And then there will be one with a half line. So possibly what we expect is that all of the tools that we have developed will just put this other case into the machine, and hopefully the machine works for us without any additional work. Because as you said, the complexity is actually smaller. Yes, that's what we very much hope. But at the moment, we didn't even try because we were kind of course, the reason why we tried the last one is because we believed, okay, that is the physically most relevant, I mean, the one you see the most, and it should also be the one which is mathematically most difficult to treat. But of course, before I actually touch it, I cannot tell you for sure.
Okay. No? Des questions? Preguntas? Thanks very much. Thanks very much to Camillo. This really great